Hello, everyone. Thank you for joining this presentation. My name is Reza Malakooti, Reservoir Simulation Engineer in CMG. As the topic of the presentation says, it's about the modeling of the geothermal reservoirs in CMG simulation suites. The main focus of the presentation would be that how the CMG simulators could be used in order to model such a kind of geothermal systems, which for that I will briefly talk about maybe the different geothermal systems that is basically available, and then by a very brief introduction to each CMG simulator that I will talk about them today. Then we're going to see a couple of examples of basically those geothermal systems that could be modeled with CMG software. So maybe if we traditionally look at the geothermal systems, we can have them in either hydrothermal conventional resources, or maybe as enhanced geothermal systems that we may call it EGS. In hydrothermal conventional resources, we've got all three elements of the water, heat, and also permeability at the same time within the system. These reservoirs mainly representing as a kind of naturally fractured reservoir. And the setup of such a kind of systems would be very much similar to basically what you may have in the oil and gas reservoirs, when you drill your wells and then start to producing the hot water, for example, from those producers, extract the heat at the surface, and then use that, let's say, energy for other purposes, and then reuse, or let's say re-injecting back that water maybe into the reservoir again for the pressure maintenance objective. While in the enhanced geothermal system EGS, we just look at a kind of a heat element available in the system. They would represent mainly as a very hot dry rock system, which means that first we need to introduce the element of the permeability into such a system by conducting the hydraulic fracturing, for example, and then by circulating the fluid such as water through a kind of injector. Then we can heat up the fluid as it contacts with the dry rock, which is hot, and then produce back from the sometimes maybe the same well or the other producers that we may have in the system. To model such a kind of systems, the physics, of course, would be very important in these geothermal systems. And as a summary of those concepts that we may consider them in that system would be, of course, the fluid flow in porous media, which is the general concept that is happening in the naturally fractured reservoir. The heat transfer concept of either in terms of conduction, convection, or dispersion. And the thermodynamics of the mixtures, water, gases, and solids, due to the presence of the, let's say, water, and also the kind of conversion from that water maybe to the vapor, there could be a kind of sometimes presence of the other minerals or salts that could be precipitated within the system. For such a cases, of course, the considering of the geochemistry would be very important, and also the associated reactions with that kind of effect. So these are the kind of main concepts that we look at them in the reservoir side, but we also need to look at the wellbore in terms of both the heat transfer phenomena and also the pressure drop which is happening in the wellbore. Of course, within the wellbore, we're going to have the conduction or convection in the along the wellbore, and also the wellbore hydraulic calculations for the pressure drop. In CMG, such systems could be modeled using our thermal compositional simulators that we call it STARS. It's pseudo-compositional because it's not using the equation of state, it's using the K-value table in order to partition the component into different phases. STARS would be able to handle the different grading systems of Cartesian, radial, and of course, the kind of naturally fractured reservoir or presence of the faults in the system would be also available for modeling in that simulator. One of the features that STARS will be coming with is the advanced well feature that we have got in STARS, and that's a kind of transient wellbore simulator that you've got that discretized, let's say, wellbore simulation model attached to the reservoir, and then have got a kind of both transient fluid flow model in the reservoir and wellbore together. And of course, in terms of the geomechanics and geochemistry, these are the features that would be also available in STARS. This is one of the standard geothermal example that we have shown in STARS, which is basically presenting the modeling of that conventional geothermal reservoir in this case. As you can see, we had the number of wells initially in the system, and that reservoir has been modeled as a kind of geopressured reservoir with typical porosity permeability value close to the range of the property that we have in Icelandic, let's say, situations of the geothermals. And then the main objective of the study was to evaluate the effects of the heat transfer, and also quantify how much the energy could be produced from such a geothermal system. We've got two different scenarios in here. In the first scenario, the left-hand side, we had just the water produced in the system. But in the second scenario, on the right-hand side, we also add the injectors, which basically replicating the concept of that reinjection of the water into the system after they have been basically produced from the geothermal reservoir. And in terms of the results, we could see a kind of plateau of the produced energy from the first scenario when we had only the water producers. And of course, with the help of the pressure maintenance, when you add the injector into the system, we could extend the plateau for a quite longer time to show basically the effects of that pressure maintenance on the performance of the geothermal reservoir. And that's basically just showing the concept of that water injection back into the system, which is basically cooling near the wellbore, and the idea of basically that reinjection of the water would be in a way that it doesn't compromise the basically heat or temperature that you've got around that producer, which these are something that could be added into a kind of optimization or uncertainty analysis when people can decide about, let's say, the location of these injector wells, or let's say, how much would be the optimum volume of the water that could be injected in order to maximize that plateau of the produced energy in the system. So talking about the optimization and sensitivity analysis in that kind of standard geothermal example, we also showed the coupling of stars with our optimization package CMOS. In that typical study, we actually examined the effect of different properties on the produced enthalpy in this example. And with that tornado plot, you could see the effects of different property on the produced energy, which is basically depending the way that we set up this model. The main parameters in that example that we could see had a very high impact on the produced energy was the naturally fractured spacing in here. By having, or let's say increasing the fracture spacing, as we more focus on the fracture flow rather than the matrix flow, we could see that the amount of the produced enthalpy has been reduced. In the second example, we show in here that for the hot dry rock, or that, let's say, EGS system, stars can also be again used in order to model such a system. In that specific example, we use the hydraulic fracturing wizard that we have in our preprocessor builder to make basically the kind of fracture channel between the producers and the injectors. And as you can see in here, from the injectors, we are producing the water into the system. And as the simulation times, the water would be communicating towards the producer, will be heated up and then produced back from that basically producers in here. Of course, the main difference of having such a kind of hydraulic fracturing or not having this hydraulic fracture would be the case that if we remove these hydraulic fracturings, we will see a kind of just accumulation of the water mainly around the injector and no communication towards the producer. As we said, these are a very impermeable basically system. The second class of the geothermal systems that we have seen recently coming from, let's say, a couple of companies in here is the concept of the closed systems, which is still in the early stage of the development. And they would represent a kind of a small scale power generation. But they are reliable and promising, as there is no kind of emission, or let's say there is a very small footprint out of these such a kind of systems. If we just look at the first picture in here on the left-hand side, in these closed systems with a single well configuration, people inject the cold water into the annulus, and there would be no perforation or communication between the well and the reservoir. It would be completely a kind of cased hole well. And then as soon as that cold water is coming in contact with the hot reservoir source, let's say in here, it will be heating up and then reproduced back from the tubing. Or in a different configuration in the middle, we can see that we look at a kind of injectors and producers, and these two wells would be also connected somehow together in the system. As you can see, you just inject the fluid. As it contacts with the reservoir, it will be heating up and then reproduced back at the surface. And in the third basically picture in here, which is coming from the EVOR technology concept, we see a kind of, again, the concept of the injectors and producers, but you see that the the number of the laterals could be happening between these injectors and producers. One of the main difference in basically between the third and the other, basically these two, is that for this third one, people is also interested in capturing or modeling the heat exchange effect at the surface level. While stars would be available for modeling these, let's say item 1 and item 2 in here, we cannot model we cannot use the stars to capture such a kind of heat exchange at the surface. And for that reason, we are introducing the coupled package that we have in CMG, and those would be GEM and CoFlow. Just a brief introduction on basically these two packages. On a GEM side, we look at the fully compositional equation of a state simulator, which has got mainly all the features that we have in stars, but definitely the main difference would be how the PVT would be handled. GEM would use the equation of a state, but stars would use the k-value table. In terms of the CoFlow itself is a kind of the integrated production system modeling package that by its own, it will be coming with own reservoir element, reservoir simulator, wellbore simulator, and also the surface network facility. And at the end, you're going to have the kind of implicit couple of the reservoir network and well within the CoFlow. In CoFlow, we offer different levels of the modeling for the wellbore, for the reservoir, and because it has got a surface facility, for the cases that people would be interested to add the more details of the surface elements, such as, for example, pipes, chokes, pumps, or heat exchanger, etc., that CoFlow element would be very helpful. So for that closed loop model system that I talked about as a kind of eager technology, in the example that we somehow demonstrated the concept of this technique in CMG software was that using GEM simulator to represent the reservoir and the overburden, and also the all multilaterals or the horizontal sections that you've got in the reservoir, and then use CoFlow to model the vertical wellbore sections and also any surface network that we may have in the system. So, as I said before, the element of the reservoir and these horizontal sections would be something that we take care of it in the GEM, and then the vertical sections of the injector, let's say in here, and the producer, in addition to anything that you may have in terms of the surface elements in here, would be taken care by CoFlow. In terms of details of modeling such a kind of coupled GEM CoFlow model, because GEM does not have the kind of or let's say heat transfer modeling in the wellbore like stars, we need to somehow to use the hydraulic fracturing wizard to present the horizontal sections in GEM, which that basically channel or fracture would represent a kind of lateral which would connect the injector into the producer. And then the vertical sections of the wellbore would be modeled in CoFlow. And that wellbore model in CoFlow would be a kind of a steady state wellbore simulator. In terms of the results, as we can see from here, depending on the spacing between these basically laterals, we can see the temperature front can change. When the spacing is quite basically long enough, we could see the higher, let's say, bottom hole temperature for the, let's say, fluid, as the temperature front would not collapse into each other. And that's the same kind of result, but looking at the profile of the temperature along the well, just to basically emphasizing the effect of that spacing on the bottom hole and also the wellhead temperature in here. In addition to the spacing between the laterals, there are a number of other scenarios that people can basically study by such a kind of coupling in GEM and CoFlow. People can also look at the number of the laterals, the length of the laterals, or even the pattern of the laterals, if the spacing would be uniform or, for example, non-uniform. The counter current flow could be also checked when, for example, you may, for the first lateral, put the injector on this side, but for the next lateral, you may basically use the opposite side for the injection of the fluids. And also the alternative fluids, like, for example, brine, could be also included in those studies. And finally, the third example that we want just to show you in here is just basically using CoFlow to model a kind of single well closed loop system. We did that kind of example with no reservoir model, because in CoFlow, as I said, we have different levels of the modeling for reservoir and wellbore. For reservoir, you can go for more advanced 3D static reservoir modeling, or use, for example, tank model, or just use a kind of, let's say, inflow proxy model to represent the kind of reservoir behavior. And in that example, you can see that we have somehow modeled the required completion that we had in that single well by using that, let's say, concentric tubing to capture the concept of the injecting of very cold fluid into the bottom of the reservoir, and then reproduced back from the tubing that hot fluid from the bottom hole. Maybe as a summary of what I discussed in the closed loop geothermal modeling, of course, depending on the objective and what people would be looking at, you may go for a stars or GEM. Stars traditionally would be recommended for basically modeling such a kind of systems, as you saw the examples, and also, as I said, the single well or double well, the U configuration that we showed would be possible in stars. The only time that stars would not be applicable is something, or let's say sometime, that people would be interested to capture the heat exchange at the surface facility, which on that time GEM and CoFlow would become on board to kind of model such a kind of systems. And just a kind of summary of what we discussed, we have seen in the literature from the companies, the cases that we have been dealing so far, a number of concepts of the geothermal systems. And in CMG, depending on the objective of the study, which, for example, geothermal system we are looking at, we are able to choose the right simulators for capturing the basically appropriate features that we want to see for those systems. Stars would be recommended as a kind of, let's say, simulators that you can do your modeling of geothermal system, including the conventional ones, EGS, single well, and also the U-tube configuration. But for the cases that people may want to add the surface network elements, such as heat exchanger, etc., then on that kind of things, GEM CoFlow coupling would be a kind of approach that we can propose for those situations. So with that, I think I'm basically finished with the presentation. If there is any questions, I would be happy to answer.
Thank you, Reza, and thank CMG Limited for allowing this opportunity for us to see geothermal system modeling with the software. There's quite a few questions. I don't think we have time to answer them all, although there's a 30-minute live Q&A session coming up. So let me ask just one question, or maybe two. From Syed Mohadem, does CMG have any plan to explicit simulate for explicit simulation of fractures and using finite volume method to use unstructured discretization?
In CMG recently, we have done the possibility of importing the DFN models that you may have done through other third-party softwares, basically discrete fracture networks. And if we have got that model or those models ready by a kind of third-party software, you can import them in basically CMG now and use them.
Okay. One more question, which is common as well, from Mohammed Nikpour. I would have the same question, basically. So he wonders if you know what model is used for average thermal conductivity and average thermal capacity, which is similar to a question that I would have is, instead of using average, does CMG simulator now would have a built-in stress-dependent porosity, saturation-dependent thermal conductivity, or other thermal parameters? As you understand, if it's dry, hot, dry rock, this pore space is air, which is lower conductivity than a fully water-saturated rock, okay? So it could be 10 times as high. So as the hot fluid or cold fluid going through, the thermal conductivity would change, or capacity. So does CMG, or can CMG handle that?
I'm assuming we are looking at the geomechanic effects in here, correct?
No, strictly thermal conductivity. Because it's not going to be a constant. It would change as you have different fluids in the pore space. And I asked that question of all geothermal conferences, and most people do not have that. They use a constant or average number. So I think that's something to look into. That would probably deserve some experimentation, some research, and generating some type curves or whatever.
Yeah, I think this is something which I am not sure yet if I want to give you the answer on that one.
Yeah, I think that's something to look into.
Yeah.
So anyway, there's 2 or 3 other questions on the Q&A. If you could type your answers in, that would be great.